Okay, for class 7 in static dynamics. Here's another example here with a little bit more complicated, I guess so. Path coordinates example. Very common to do a problem that's involving a pendulum right here, right? Much easier to use this stuff in a pendulum. Okay, so this was a difficult problem, actually. Yes, this is a difficult problem where we have a pendulum here, and we want to find the tension in the string when theta is 0. That's like a really easy problem, right? Now the hard problem is going to be to find the maximum angle that this thing will achieve, and we'll see where that becomes a difficult problem. So we need to be told, we need to be given something. I think, right as to this point. Yeah, no, we were given that this is 4 meters per second at the bottom, 30 kilograms, and it's 4 meters long, right? So that's the given. So let's figure out when it's down here what its tension is going to be. I already have the free body diagram and the IBD drawn right in there. When it's at its bottom, the velocity is at a maximum and acceleration is 0, right? Right here when it's at its bottom. It's kind of hard to like picture that, but you gotta have a maximum, a minimum. It's not accelerating just yet. As it gets a little bit further over, it's gonna decelerate. But right here at its bottom, its velocity is a maximum, so its acceleration is 0. And so we have weight, and we have, and I wrote this as T. I prefer to write FT on my stuff. I don't like that. And so we know the mass times acceleration in this direction. So we have all of that already set up. So it becomes a pretty easy problem right there in the tangential, not tangential, in the normal direction. And positive is going, this is the center of the path, right? So it's going upwards, that normal. And it's going to be mass times acceleration in normal direction, and we know that happens to be mv squared right there. So taking a look at right here, we say that ft minus the weight of the thing, those are all the forces over there in the tangent normal direction, keep saying tangential normal direction, and it's going to be equal to mass times velocity squared in rho, right? So we want to find that tension. And we have mass, I wrote mass mg right there. Should have wrote this as equal to mg and just written that as mg. So we have 30, and we are in SI, so it's 9.81. 30 right here, and velocity is 4 squared. The length is going to be the curvature right here of the arc. So we get a tension that's going to be equal to 414 newtons. We can even say it's a tension right there. That's good. Now becomes the hard part, right? And this happens with many problems involving like a pulley, or involving something where we don't know an angle. We draw it at an arbitrary angle. So let's draw our FBD and our IBD of this thing at some arbitrary angle, and it's best not to use 45 right here. So here's vertical, here is the angle at which that we're going to be, and so the tangential ET is that direction, and EN is this direction right here. So right there is going to be the tension FT that we're going to have right here. Here is going to be the weight of the thing, right? And so we can see that that's the angle. Here's the angle that's happening right here. Here's the angle on the piece, and right there is the angle. You know, we can have all those things. All right, so it's going to be equal to, and we're going to have these aligned here. So it's mass times acceleration in normal direction, mass times the acceleration to tangential direction. That's right in there. And at its maximum, right, at its maximum angle, that becomes 0 right there, right? That's something that we're going to know. oh, the velocity does not, oh, sorry, acceleration does not equal 0. Sorry. Acceleration is 0 down here. Acceleration is not 0, but the velocity is 0 right there, right? So, so this is, I'll write this out, at the maximum angle right in there. So what we'll say, let's say the sum of the forces in the tangential direction, right there, right? And oh, and by the way, at this time this has to be equal to 0, right? That doesn't really help us with anything, but it would be true because the velocity is 0. This acceleration is going to be 0. So these things would actually, we would know what the tension was. It doesn't really help us any. So we go in the tangential direction, and we say mass times acceleration in the tangential direction. And the acceleration is actually going to be at its peak right here. It's actually probably should be, it's a deceleration just before it's happening right up here, but it's about to, I think it actually should be probably going in that direction right in there as part of this. Yeah, interesting. Yeah, so it should be, anyway. So let's see, I'll take my positive as being this way right here because it's tangential. So I say I take my weight is going to be in that direction, right? So here is the direction about which we're dealing with the thing in the tangential direction, right in there. And I made it look a little bit too much like it's 45-degree angled again. So I'm going to take negative weight times this thing times the sine. Is that right? Yeah, the sine of theta. And it's going to be equal to mass times the acceleration in the tangential direction. We're going to see that we have mg sine of theta is equal to mass times acceleration at tangential. So this is telling us that the tangential is going to be negative right in there. And also notice that mass cancels out right here. So we establish that this is true. Negative g sine of theta. So this is like opposite to what we had, how we had drawn it. Now, if we want to try to find out what its maximum angle is going to be, we're going to have to try to find when the velocity is equal to 0, right? So we want to turn the acceleration is a function of angle, though, right? But we do know, right? So the thing that we know is that the tangential acceleration right here along the path is going to be dv ds. We need to have something in here in terms of angle in order to use this, because acceleration here is a function of angle. We want to try to find when the velocity is going to be 0. That's going to allow us to figure out what that maximum angle is going to be. So we have to do some manipulation. I draw over to the side right over here that we will have, I guess I'm going to do it arbitrary, right? So this is going to be an arbitrary little segment right here, right? Okay, so that segment is going to be ds. That's in there, right? So I wrote delta s. I meant to say ds. All right, so that's going to be the length that happens of that segment. Here is, I'll call it rho, and inside here is d theta right there, right? So what we can say here is that ds is going to be equal to rho times d theta, right? That's that arc length is placed right in there. So when we say this right here, we can replace ds with rho d theta as part of this. So we can say that the tangential is going to be the velocity divided by rho times dv d theta. Let's put this back up into here. All right. So this is what we were told from our sum of the forces right here. So let's put this knowledge to use, and we could rewrite all of this right here as saying AT times rho times d theta. All right, so this rho d theta is equal to v dv, and we can integrate. And we can integrate from the two extremes, right? So we know here it's going to go from 0 to theta max. From here it's going to go from 4 to 0. That's the thing we want to try to find. So now we're going to be able to figure out what theta max is by sticking that back in there. I think I went ahead and I left, okay, no, I'm going to leave this as negative in there. So we take the integral from 0 to theta max, substitute in the negative g sine of theta, d theta, and of course I'll just write this again right here. And we integrate this, and we're going to get, we know we're going to get, integrate a sine, we're going to get a positive cosine. So we get a g times the cosine of theta. We also need, I forgot my rho, right? So there's a rho in there. There's a rho right in there. So I forgot to bring him back over into there. And this goes from 0 to theta max, right? And that goes from equals 1/2 v squared from 4 to 0, right? So if you go through and we put these things in here, and we know this is going to be 4 meters, that's 9.81, and the cosine of, let's see, 0 here, we got to be careful of this, right? So we have the cosine of theta max is this one, but it's going to be minus 1, right? Because the cosine of 0 is 1. And that's going to be equal to 0 minus 1/2 then the v 4 squared. I'm sorry, I cut the thing out. So we're able actually to get the v max is going to be 37.24 degrees. That's a pretty good outcome right there. We could figure out this. And we could use this is much more complicated thing. We could do this problem again when we use work and energy. We could find this going to be much easier to do. But this is using in path coordinates to be able to solve the seemingly easy problem to get this maximum here. But we're also, it's using the kinematics as part of this, and you could see that the kinematic relation, this relationship that we normally would just be given in kinematics, right? We would just say, okay, acceleration is a function of theta. Well, where did it come from? It came from using the path coordinates in a kinetics problem. So hopefully that isn't too confusing, but it's a little confusing. It's useful though.